All right, we are marching on through our look at various techniques of integration. Last lesson was integration by parts, which was really straightforward, really cookbooky, very recipe-like. This is similarly process-oriented. The process can be a little bit more difficult. We will look at integrals of powers of trig functions, and so I'll just sort of let us know where we're going. The first bulk of the video will deal with integrals of the form sine x to some power cosine x to some power. This is what we deal with in the bulk of the video. There are three cases. They basically form a flow chart. You see if the thing is a case 1. If it is, great. Otherwise, you hope it's a case 2. If it's not, then it's a case 3. So in our flow chart, case 1 is the case where m is odd, where the power on sine is odd. So it doesn't matter what this is. If the power on sine is odd, this is case 1. And the key in this case is to break off a sine x and use the fact that sine squared x is 1 minus cosine squared x. That's the key. We break off a sine x, and we use the only Pythagorean identity that you remember from your high school trig. Sine squared x is 1 minus cosine squared x. So, for example, the integral of sine cubed x times cosine to the 4th x dx. If this is your integral, then we break off a sine x, and we use this fact. How? Well, this is sine squared x cosine to the 4th x sine x dx. If that is the case, then this is going to turn out to be your du. We want du to look mostly like that. Well, how do we do that? Well, if u is cosine x, Schmigen, so sorry. If u is cosine x, then du is pretty much this. Du is the negative of the sine of x dx. So now we're hopeful. That's a minus. That's a minus. Now we're hopeful. The problem is u is cosine x. That's u to the 4th. What's that? Well, sine squared x is 1 minus cosine squared of x. Otherwise, everything else remains the same. So what is this? This is negative integral of 1 minus u squared, u to the 4th, and then all of this is du. So what is that? This is the integral of u to the 4th minus u to the 6th du. And we know how to do that. That's 1/5 u to the 5th minus 1/7 u to the 7th plus a constant. And what was u? U was cosine of x. And you got it. This will work every time. Every time the power on sine is odd, you break off a sine x. This becomes your du. And then you get everything else in terms of cosine because cosine x is the u. Then you get a polynomial with cosines. Those antiderivatives are easy, and you're done. Every question where the power on sign is positive runs this way, which brings us to case 2. So what if the power on m, the power on sine, is even, but the power on cosine is odd? Well, in this case, the key is to break off a cosine x and use the fact that cosine squared x is 1 minus sine squared x. And you're thinking to yourself, I think we've played this before, and we have. So let's just show what that looks like. So the power on sine is even, so it's not case 1. The power on cosine is odd, so it's case 2. Well, what do? We break off a cosine x dx. Why? Why do we break this off? Because this is going to be du. And this is going to be du if u is sine x. No problem with the plus in front here. No problem with that. So u will be sine x. Well, that's great. That's u squared. But what's that? Aha! Aha! So now we can make the substitution. This is the integral of u squared times 1 minus u squared, and all of this is du. Well, how do we do that antiderivative? Well, we multiply through first so that what we have is a polynomial. And then I know how to take the antiderivative of u squared, and I know how to take the antiderivative of u to the 4th. And so subbing back in is really straightforward. And you got it. It is very similar to case 1. So basically, if we can, we break off a power of cosine x. If we can, we break off a power of sine. We just put one of them at the end. That becomes the du, and we're in great shape. It's this one that's a bit of a mess. This one's a bit of a mess. This is the case where m and n are even. And if this happens, the key is to remember that sine squared x is 1 minus the cosine of 2x over 2, and cosine squared x is 1 plus the cosine of 2x over 2. One of those is going to be necessary. We're going to need at least one of those, maybe both of those. What do I mean? Well, let's pretend that our example is integral of cosine to the 4th x dx. The power on sine is 0, that's even. The power on cosine is 4, that's even. So we want to use these things. Well, probably not this one, probably this one. So how does that go? This is the integral of cosine squared of x squared. And that's the integral of 1 plus cosine of 2x over 2 squared. So I'm going to do two things simultaneously. You're not going to like either of them. I'm going to square this 2 and pull it right out so that what we're left with inside, we just expand the brackets, and that's 1 plus 2 cosine 2x plus cosine squared of 2x. That's just expanding the brackets. You might have called it FOIL when you were young. So I'm hopeful because we can do this. We know that antiderivative. We can even do this. I'm pretty sure we know that antiderivative. It's this one that's tricky. And it's tricky because it's got the cosine squared in it, but then what we do is we just use this again in a creative way. So I'm going to leave everything else exactly alone. Then I'm going to recognize that the cosine squared of a thing is 1 plus the cosine of twice that thing over 2. This is 1 plus the cosine of twice that thing over 2. And so now we can actually do this. The integral of 1 is x. The integral of 2 cosine 2x is sine 2x. The integral of 1 is x, and the integral of cosine 4x is 1/4 sine 4x, and we've got it. This is by far the hardest case because remembering this is difficult, and then squaring this requires a repeated use of the identity. So algebraically, trigonometrically, this is the disaster. By contrast, powers of tan x and secant x are much nicer to work with. The key here is to use the fact that secant squared x is tan squared x plus 1. Or if you like, tan squared is secant squared minus 1. I mean, that's the other way to do it. So just a couple of quickies here. When you're trying to do the integral of tan squared x dx, you ask yourself, tan squared x, that's secant squared x minus 1. But wait a minute, I know what that is from Calc 1, and I know what that is from Calc 1, and I've got it. Or you wonder aloud, let's see, this looks like something where I should break something off and make it be a du. The derivative of tangent is secant squared. I don't have a secant squared. But the derivative of secant x is secant x tan x. So maybe that's du. Well, that's only du if secant x is u. And secant x is u if I can make this look like a secant x, and I can. And if that's the case, this is u squared minus 1 du. And we know how this goes. Oh, maybe you know how this goes. I'm apparently still learning. We know how this goes. This is 1/3 u cubed minus u plus a constant. And we know what u is. U is secant x. And we've got it. So I have a few things for you to consider before we gather. You should try to find the integral from 0 to 2 pi of sine squared x dx, and the integral from 0 to pi over 2 of sine cubed cosine squared, and the integral from negative pi over 4 to pi over 4 of secant x to the fourth. I will tell you that one of these integrals has the value 8/3, and one of them has the value pi, and one of them has the value 2/15. And you should figure out which is which, and our 15 minutes are up.